Okay, so those of you in week 13, you guys can take control of the screen share when you're ready. We can get ready to start. So I think you all can see the slides from the link that Evan posted. So it's all there. So I think, let's see, do we have I think, yeah, Evan, Zihan, and Henry are going first, I guess. And then we have Shreyas and Yong and Ruofan presenting the second work. Yes. So it looks like we have just two papers covered today. Is that right? Anyone knows, then you can let us know.
Yep, just two papers.
Okay, great. So it'll be a nice shorter session and we can wrap things up a little early as everyone's pretty busy for the last section. So those of you on Scribes will have an easier time because there's only two papers. So make sure you take a look at the slides. Sorry, the Scribe notes, which are, I think, already circulated from before. So I will put them up on the channel as well. Okay. Okay, yeah. So Evan already put it up. That's great. So you guys can go ahead. So Evan or the rest of you, when you're ready to screen share, you can go ahead.
Right, I'll do the screen share.
Okay, thank you, Henry.
Can you see my screen?
Yeah.
Okay, great. Let me put this into a presentation mode. Okay, great. Yeah, this is conversational recommendation system, session 3. Okay, so the first paper that we will be reviewing is on the topic is on the towards explainable conversation recommendation. So this is the paper is being submitted to the accepted in ICJRI in 2020. So the presenter will be three of us, Evan, Zihan, and myself. Okay, to start off, the outline of presentation
have a
will be
window that's on top of your slides. On the Zoom, it seems to say that there's a window.
Yes, I tried to
application.
get rid of this, but try to get rid of this.
Is it a window from another application?
No, it is the not sure. Let me stop sharing and sharing again.
Okay. Yeah, maybe that'll make it easier to see.
Is it better now?
Yeah, the window is gone.
Yep.
Okay, great. Yeah, I was confused as all the box there. Okay, right. So the outline of presentation is will be three-part. Introduction will be presented by me. Proposed models break into the two proposed model. One will be presented by Zihan, another one will be presented by Ivan, and later he will present on experiments as well. Okay, so to get off with in terms of the introduction on the ECR, the accuracy is important when it comes to recommendation. as well as the explainable is now is also is topic now is also is called is essential for the recommendation. So what we mean by explainability is explainable. So what we mean by explainability is that it requires that the system to provide some kind of explanation of why certain items has been recommended. So why is it important for explainability? Because the explainability will help the users in terms to improve the user satisfaction, as well as it will build the trust for the users for them to trust the system. So the advantage of using explainable to provide explanation is it will help the users to understand the systems better. And also the second aspect of it is that by providing explanation, the system will then expect the users to provide the feedback to the system, which will then later they will provide the feedback whether the recommendation is either wrong, or the system will then be able to take the user's feedback to further improve the recommended item back to the user. Right. So to give the example of what is the ECR is, this is the example of the interaction between the users and the ECR system. So for example, the model will first give a recommendation. So the highlighted in underline by the underline is the predefined template. The green box is basically represented as recommended items to the users, and the red font color is represented as explanation why a certain item is being recommended to the user. So for example, the model is that, okay, I recommend this particular film. And in terms of the explanation, it is to explain what is this recommended item is. For example, this Pulp Fiction is a dark comedy. So for the users, they will be able to see, oh, okay, so the explanation of what is this item is. So they'll say, oh, no, I'm not looking for the comedy right now. So therefore, the recommendation system will then take feedback of this particular dark comedy or the concept here, then they can remove them out from the recommendation back to the users until when the users is satisfied with the recommendation. So this is just example of the the interaction between the user and the ECR models. So to give the context of why the importance for ECR is that the ECR provides explanation to help users to understand the models. They also collect and integrate users' feedback into the explanation recommendation in order to provide like a bi-directional communication through the conversation. So this recommendation and explanation are mostly an iterative process, and it redefined every times when the system recommend items to the users and receive the feedback. So in terms of the methods of how the feedback is collected from the users is that in this paper it provide two methods. The first method is based on the what question, and the second is based on the whether question. So in terms of the what question is basically is a definition. In terms of what the user question is basically example is the system will then just ask a specific question whether what categories of movie do you like, or what sort of movie are you interested to watch at the moment. So this is more on the what question. The advantage of this is that this is effective for the users who have a clear ideas in terms of what are they looking for. However, the potential bottlenecks here is that this is less friendly if, for example, users still is wondering, don't know what to watch. So therefore, this is more disadvantage for this type of users. So by knowing that, the second type of methods to gather the user feedback is based on the whether question. So it proposed to the users specific movies and whether is the person like or dislike this particular features of the movie that is being mentioned. So the advantage of this is that it might trigger user to come up with something that is that the users might like. So the whether questions are the one that is adopted by this paper, and it's based on the template that I've shown earlier as well in the comments. So in terms of The key objectives that the ECR is trying to achieve is based on the three objectives, objective 1 to 3. So first objective is that it needs to efficiently integrate the user feedback in order to improve the recommendation accuracy. And the second is that it will improve the recommendation explainability. So the third objective in this case is that it should seldom or should not violate the user's requirement based on the user's given feedback. For example, if they say they do like comedy, the system should not recommend a comedy movie to the users again. So these are the three key objectives, which later will be used for the evaluation in experiments. In terms of, so the next section that I'm going to go through is in terms of the workflow of the explainable recommendation system, the conversational recommendation or the ECR. The workflow is shown in the left image here. So if we focus on the orange box here, these are basically the input to the explainable the ECR system. So it consists of two items. First is the user information with a set of information in terms of the review that the users have written. The second set of information is based on the item V, which is the set of the review of this specific item V. So the output of this the ECR system is that it will be based on recommended based on two things. First one is the set of the recommendation score of how you likes V, and the second bit of it is the explanation of the linguistic explanation of the recommendation of these specific items. So the detail of this ECR system will go through later in the next section. But here I'll just go through overview of what the workflow is like for the ECR. So after the input is given, after we get a set of the recommendation score and explanation for all of the items in the list, the next is to get the maximum function, which is highlighted in red here. This is in order to retrieve the biggest recommendation score among all the items that is been that's in the item list. And this, based on this, we will return back to the users of the top recommended score together with the explanation. Yeah, example of the how the recommendation and the explanation is shown here. So after the users have a look at this, and they will provide a feedback whether they like or dislike this item. If they dislike this item, the users will provide in terms of the free form the natural language feedback in order to give the reason why they like or dislike this particular items that has been recommended. So at the end, after through each of the iteration, this feedback list will then keep on increasing. Like for example, in this case, C is represented as a concept. The concept here is, for example, is a genre of the movie. So if, let's say, if the, for example, in this case, like you can see in the image on the left here, the concept that is recommended to the users is documentary type of movies. So based on the users' feedback, this list will be updated based on whether the users like the concept. So yes, I like the documentary, or later they will say, no, I don't like the documentary, then the concept will be I. Or alternatively, if they don't have any preference for the documentary, but they don't like this specific items, like this particular movie is Last Standing, then the item of the feedback list that has been given here as V minus here as represent as items that the user doesn't like. So this is an iterative process. It will be until the users satisfied with the recommendation, or after a number of the iteration has been reached to the maximum. So yeah, so these are the overview of the workflow of the ECR system. So the next bit is on the proposed model. I will hand over to Zihan to present.
Thanks, Harry. Can I share my screen?
All right. Okay, I'll stop sharing. Okay.
Okay, while Zihan is sharing screen, do we have any questions so far? So especially from our undergraduates, do you guys have any questions? So in particular, this framework is very similar to another framework that we heard of at the beginning of the semester. Not so much explainable, but very similar to EAR. So I'm wondering whether you guys can also highlight that the differences between EAR and ECR in your comments later when you summarize up. Okay, Zihan, go ahead.
Thanks. So I will talk about the architecture of this model. So basically it consists of two parts. The first part is called incremental cross-knowledge modeling. It learns the cross-knowledge between a given user and item pair. And it selects some important concepts select some important concepts, then fit into the next part, which is called incremental multitask prediction. And this model is doing two tasks, giving recommendation score and explanation. And overall, this model is incremental framework because we can update the model according to the feedback in each turn. And for the first part, incremental cross-knowledge modeling, the cross-knowledge here refers to the concepts. And this part consists of four modules. The first module is this embedding module. So for each user we can collect the concepts that appear in the reviews of this user and construct embeddings for each concept. So here, the concept embedding is a concatenation of the word embedding and the context embedding. And the context embedding is computed by averaging the review embeddings. So the reviews are those reviews of this user containing the concept CUI. And then the embedding of the review is calculated by summing up all the word embeddings in this review. And so far we can construct a concept embedding for a user U, and we can do the same way for item. And so far we have the concept embeddings, and we can feed them into the next module called attentive concept importance modeling. So given the concept embeddings of user and another set of concept embeddings of item, we can calculate a co-attention weight matrix to model deep user item interactions. And in this weight matrix, the entry ij is calculated by this formula fc transpose w fcvj. So cui is the concept I in the review of user U, and CVJ is the concept J of the review of item V. Then WC is a learnable weight matrix, and F is a neural network. And in this way, we can obtain a importance vector A and B. So A is for user concept importance and B is for item concept importance. And this is to find the concept with the maximum co-attentions. And here is a formula for AI and BI. So we find the concept with the maximum co-attention, then apply a softmax function to them to ensure the summation of AI is 1 and same for BJ. So here, since the summation is 1, we can represent AI as the probability of a concept I, that this concept I in the review of user U is important for this user item pair. And concepts with larger value of this importance AI tend to be selected at the end of this part. Then since we already have importance, we think the C plus and C minus can serve as ground truth labels for important and unimportant concepts. So we can construct a concept level feedback clause defined here. So in this formula, the A plus refers to the concept C plus in the feedback, and A minus and B minus refers to C minus in the feedback that the user dislike about. And yeah, so we can consider minimizing this loss function as a global view of this incremental learning, as it helps improve the concept embeddings and other parameters of the model. But the drawback is this loss function may tend to reduce the importance of these C minus concepts. So we say that the impact of this loss function on AI and BJ is sort of indirect because the impact can only be achieved by changing the parameters of this weight matrix. So to fix this problem of indirect feedback integration, we will use local label propagation in this module. So we construct two aggregated embedding, and we do a propagation based on the distance of the concept embedding to these two aggregated embeddings. So in the formula of the aggregated embedding, we take a weighted sum of the concept embedding average and P plus. So the P plus is the value of C hat plus in the previous term, as we are updating this model with the feedback in the current term. So we definitely have a C hat plus for the previous term, and the same for C hat minus. And alpha T is a learnable parameter to balance between the current and the previous feedbacks. And now we can compute a preference score beta C of the concept C based on the distance to these two aggregated embeddings. And this score attains maximum when C is equal to C hat plus, and attains minimum when C is equal to C hat minus. And with this score, we can calculate the local concept importance vector A prime and B prime. And now we can combine the global importance and local importance to select some important concepts. So in this module, we calculate multi-view concept importance AI bar and BJ bar, which is a weighted sum of AI and AI prime. So AI is from the first module for global importance, and A prime and B prime is from the local importance module. And with this multi-view concept importance, we can construct another loss function which is similar to the previous concept level loss. And the only difference is we replace the global importance with this multi-view concept importance. And now for based on A bar and B bar, we want to select some concepts and to include them in the explanations and the recommendations. So to avoid the non-differentiable prediction, we use this straight through Gumbel softmax function, which is defined here. So it's a variation of softmax by manipulating the logic with taking a log and add some noise. And the output of this Gumbel function is a one-hot vector, where the concept whose corresponding entry has value 1 will be selected by this Gumbel function. So we can see in each run of Gumbel, we can only select one concept. So in order to select multiple concepts, here we can run the Gumbel function multiple times, but with different value of noises here, and also change the parameters in the weights matrix. And as a result, we can select multiple concepts for user U and item V. And here is the end of the first part. So we make use of the reviews of the users and items, and also the feedback provided to select some important concepts related to the user item pair. And we will now feed them into the next module to make recommendation. So we predict this recommendation based on two views, global view and local view. The global view is based on all the samples, and local view is based on the local user item interest provided in the feedback. So in the global view, we directly use the score function in the FM model factorization machine. And before that, we need to construct embeddings for users and items. So for user, we use the embeddings of concepts and apply a parameter matrix and plus a vector, and apply a sigmoid function to get a embedding EUI. And also we think that so far we only use the embeddings of concepts. We think these concepts may not be able to capture all the information of a user. So we also add an implicit factor for this embedding. So the final embedding of a user XU is a concatenation of EU and HU. Then we concatenate the embedding of user and item into vector Q and use this Q to calculate the recommendation score. And since FM can be pre-trained with some offline training instance omega U, so here omega U is sets of items that the user likes. So we can construct another loss function based on this training instances, where U prime is a positive item that the user likes, and V double prime is a item that the user dislike, and we can obtain this item by negative sampling. And similarly, we can find a V minus, which is an item that the user dislike in the feedback. So we can use this V minus to calculate another loss function, LRF. So so far is the recommendation score for the global view. And for the local view, we can compute a recommendation score based on whether this feedback is satisfied. So we directly set the recommendation score R hat to 0 if the item is B minus, means it's an item rejected by the user in the feedback, or if none of the C plus concepts is contained in the reviews of this item. And otherwise, we set this score to 1. And now we can calculate a local recommendation score by combining R hat and tau UV. So R hat is this user item interest, and tau UV is the R hat R prime UV score in the previous term. And with the local score and global score, we can combine them using a weighted summation and to obtain the final recommendation score. And with this score, we can use this loss function LSF to learn the final score. So this is similar to this LRF, except we replace the score R with the final score R bar. And that's how we can make recommendations. And next, Evan will talk about how to generate explanations.
Okay, let me share my screen. Okay, yeah, so like Zihan mentioned, she explained how we arrive at the recommendation score, but we can actually also use the concepts that are selected by the model to generate the explanation portion of it. So, all right, okay, so for the constraint explanation generation, there are two parts to it. First, we apply, we consider two kinds of constraint. The first is a hard constraint, where we use this to ensure that the first selected concept from the model must appear in the explanations. So how we do that is we apply a bidirectional GRU, and where W and WV are the weights for the item and from user. And then we also apply a negative log likelihood loss. And this is actually found in quite a few other papers as well. And the other constraint is a soft constraint, which is intended to punish the model if there are any selected constraints that are not included in the explanation. So in this concept relevance loss, we denote the selected concepts as S, and SK is 1 when the kth word is a concept that has been selected for the UV prime pair, and otherwise it is 0. Okay, so how the learning process works is that first, the model is pre-trained with offline data, and the local view is disabled. So the model just trains on the data set with the global view that Henry mentioned earlier. And then when a feedback is provided, we incrementally update the model. Okay, so for the experiments portion, the authors experimented on 3 different data sets. One is electronics, the other one is movies and TV, and the last one is Yelp. But most of the benchmarks, the diagrams that they showed are for electronics, and we'll cover that later. So for each of these data sets, they were split into train validation test splits of 80%, 10%, and 10%. And the training set, which we mentioned just now, it's used to derive omega U, which is used in the pre-training with offline data. And where omega U consists of the items that the user U provided reviews for. And the validation set was used to perform hyperparameter tuning. And the test set was used in their benchmarks in order to simulate conversations. So the goal of the model here is to try and predict the ground truth item as well as a good explanation for it. And it does this iteratively, like what Henry mentioned. So if in the first conversational step, the model is unable to do so, we then provide user feedback to try and guide the model in the right direction. Oh, that's weird. Okay, so so before I go more into the experiments, but we'll talk a bit more about the concepts. So like Henry mentioned, concepts are things that a user could like about an item. So in this example, toy example that the authors provided, concepts are things like comedy, anime, or action. So there are things about an item, the item being like Pulp Fiction or Ice Age or Mission Impossible that a user could like or dislike about it. So one difference from this paper from others is that in this work, they actually use the ground truth explanations as the ground truth concepts rather than directly using the concepts as user feedback. So that's a small difference from this paper and the others. And so in the conversation, we assume that the user is looking out for a particular concept, CI plus, and that a user will accept an explanation if it contains a concept that's similar enough to CI plus. So how do we define similar enough? So we actually calculate the consigned similarity of the BERT embedding of CI plus against the other possible concepts in the dataset, and we sort them. So if in a recommendation there's a in the explanation, if there's a concept that is one of the 20 most similar concepts to CI plus, it will be considered as accepted by the user. And we also assume that user will point out if there's an unimportant concept that's brought up in the model's explanation. So that's CI minus. So there were two baselines that the paper used. However, they were not able to find any usable existing works, and they instead extended two explainable recommendation models to try and support the incremental learning across conversational steps, as well as try and model concepts. So the two papers are neural rating regression with abstractive tips generation for recommendation. So that's referred to as NRT, and quantitative multitask learning for explainable recommendation. So that's CAML. And both of these models were trained with BRP laws and parameters from their respective papers. So the metrics that are used in the paper are hit ratio, normalized discounted cumulative gain, and mean reciprocal rank. And these are calculated for top 1, 10, and 100 recommended items. And we also use other metrics to evaluate the quality of the explanations. And two of the calculations used are BLEU and ROC-L. And the paper also introduced this concept level feedback satisfaction ratio, but they didn't discuss how it's calculated or how it works. So in the experiments, other than the two baselines, the authors also provided benchmarks for a version of the model that considers the global view hours, which is called hours G, as well as a version of the model that only considers the local view called hours L. So, okay, so these are the experiment results from the paper, and some gleanings we can make from it are that firstly, the concept level feedbacks are useful for model improvement. So how do we know this is that in NRT, they were not able to model, sorry, NRT doesn't have the concept of modeling concepts. So it by the model hours performing better than NRT, we can it maybe suggests that the concept level feedbacks are important. And also the multi-view feedback integration is also beneficial because ours performs better than ours G, which only considers the global view. So we can see that by incorporating both the local and global views, it does contribute to a performance improvement. Okay, so these are the results for a simulated conversation. So on the y-axis, we have the recommendation accuracy, and on the x-axis, it's the number of conversational turns. And here, the y-axis is the explainability measured by ROC-L. So compared to the other models, can see that the implementation in this paper is somewhat better, and you can see that there's quite a large improvement in both the accuracy and explainability. And on the electronics data set, for some reason, after the first conversational turn, the explainability kind of plateaus. So I guess not too sure why, but my guess would be there's only so much you can do to explain why something is the way it is. So perhaps this is kind of like the upper limit of what it could reach. Okay, the authors also performed some human evaluation. So what they did was they first generated 100 test cases from the electronics dataset and generated explanations for each of for the NRT, CAML, and the paper's models for 5 conversational conservational turns. And they used 5 human assessors to annotate the explanations based on their fluency and usefulness. So for the model in the paper, it's slightly higher than CAML and NRT, and the usefulness is also kind of better. Okay, the authors also performed ablation analysis, whereby they introduced a model hours P and hours N, whereby hours P only considers the positive user feedback, while hours N only considers negative user feedback. So at the looking at the different views first, you can see that when incorporating both the local and global views, it performs better than either the global view model or the local view model. So that's one thing you can take away. And you can also see that the hours model is able to leverage both positive and negative user feedback, as it performs better than both hours P and hours N. So in conclusion, the ECR framework detailed in this paper performs better than existing explainable recommendation methods like NRT and CAML. And the results suggest that this could be due to better use of concept feedbacks from the user, especially the combination of local and global views in the conversation. And it also enables a much faster improvement in recommendation accuracy and explainability. So why this is important is because in the conversation, we don't want the user to have to go through 5, 6, 7 conversational steps in order to arrive at a conclusion. It's best if within one or two messages, a user can arrive at a reasonable answer. So this is important. So yeah, that's it for our part. If there are any questions.
So let's thank all of our presenters, Henry, Evan, and Zihan. Do we have questions from the floor? I know it's the end of the semester and you guys are busy, but we'll pause for a while since we only have 2 papers, so it would be better to have a longer discussion on this. So we'll wait for a while for you guys to ask a question or two. So maybe you guys can go back and help us understand some of the decision making in this paper. So are there alternative ways that the authors thought of that they didn't execute for doing the explanation? So in particular, they use a hard constraint just for the first selected constraint. Were there cases where they could have used multiple constraints as hard rather than soft? So you go back a couple slides to where you talk about hard and soft constraints, right? They are using just a particular feedback for the first concept as the hard constraint, right? Is that correct?
Yep.
Okay. And this selected concept, it must be a positive concept, or can it be a negative one as well?
I guess it could be a negative one as well, because if you apply it negatively, I guess you are helping to eliminate the concepts that are not important to the user.
Mm-hmm. So I think in your example dialogue, there was a case of that, right? Where the user says, I'm not interested in documentaries or something like this. So
yes.
That's an example of a negative feedback, right? Okay. Yep. Questions from the floor? We've got a good 10 minutes or so, so it's been nice to have some discussion. So, I mean, we can contrast to this other paper that was discussed at the beginning of the semester, which was the ear paper, right? This is the a paper that does a similar type of recommendation process by trying to match concepts. So maybe we can you guys try to summarize what are the key differences between this paper and the other one?
Henry or Zihan, maybe you could try and.
And it's okay if you cannot answer. I mean, this is the whole point of the course is so we can discuss. So can you guys point out, or maybe Yisong or other people who were on the ear paper and presenting the ear paper, you guys can also chime in to say why.
I guess one key difference would be in the estimation action reflection paper. The model has two actions available to it. The first is to recommend something, and the other is to ask. But in this paper, the assumption is that it would always do a recommendation, and I guess the ask is assumed to come from the user from their negative feedback, being that like they don't want to watch a comedy right now, for example.
Right. So the preference must is elicited when giving the system feedback, right? So it's implicitly asking when the user gives feedback. I think another crucial difference that you can see in this paper is it has a difference between the local model and the global model, right? The global model is the multi-view FM model, and they have this learned offline for the most part, right? And then they're doing the recommendation using local perturbations for the particular session, right? So maybe I can invite those of you who reviewed the ear paper. How does that particular process differ between the local and global views compared to the other previous papers where we saw a handling of, let's say, both positive and negative feedback? We've seen a couple cases of which there's asymmetric handling of positive and negative feedback. Can I invite some of our undergraduates to take a shot at this? What are some key differences that you guys remember from the other papers or your projects that sought to replicate some of the outputs? How you handle positive and negative feedbacks from user? Nobody wants to take a shot? Maybe I'll ask our current presenters or the scribes. So we have a bunch of scribes today. So those of you on the W13 channel who have been following Evan, Zihan, and Henry's presentation, do you have any comments about how different models, not necessarily this one, handles positive and negative feedback differently? Gabriel, yeah, go ahead. give it a shot if you don't mind. Okay. Nobody wants to discuss. You guys are very quiet. Okay, maybe we'll have to defer to our scribes. So then our scribes in week 13, do you have any viewpoints about how to handle positive and negative feedback and why it should be handled either symmetrically or asymmetrically?
Well, I was just looking at the objectives that they described for ECR right at the beginning, and one of them states that one of the objectives was that you should seldom violate a user requirement that's reflected in the feedback, which indicates to me that when the user has a particularly strong feedback that's negative, saying I don't want to watch X, Y, Z, that the recommendation should never reflect that. It seems to be an argument to me as to why the handling of positive and negative feedback should not be symmetric.
Okay, thanks, Sashankh. So in this paper, are the works being handled symmetrically or asymmetrically?
It's asymmetrically.
Asymmetric. Can you give us more of an explanation why? I mean, we see there's a difference between the local model and the global model, but and the fact that the hard constraint caters for the first concept, right? Selected concept, but how is it being handled asymmetrically in this paper?
So if you can go to the multi-view recommendation for the local estimation slide.
Is it here?
Previous right. One was no, sorry, one slide after. One more. Sorry, maybe a few more next. Yes, correct. So here,
okay.
if we see the in terms of the local estimation is that the code at the middle area there, that's where the system will either put 0 or 1 otherwise. Yes, that bit, correct. So you put 0 or 1 otherwise. So what it means is that if there's any particular strong items that let's say if there's any specific concept that the user like so let's say for example, if the user is interested in action movie, for example, then by using the localized approach, it will drop all of the items that does not have this particular concept that the user likes. So yeah, that's my view of why is it being handled symmetrically.
Okay, thanks so much, Henry. So this seems to be the case for the previous term, but is this propagated over all of the terms? So this set enlarges over time? Yes. So it's yes, you don't revoke a previously negative selected concept. It keeps on incrementally enlarging. Okay.
So maybe
Please
one of the thing that I would like to bring up for the discussion as well is that if you see the feedback on top there, which will incrementally increase, we can see that there's a C positive, the concept that is positive, and there's also a concept that is negative as well as there's items that the users is particularly dislike. So one of the things that I'm thinking is that why the author does not include the V positive. Let's say, for example, if I give the context is that, let's say, for example, if the system recommend, oh, do you like a Mission Impossible? It's an action movie. The users could answer that, yes, I like Mission Impossible, but I have watched them. So this will be, this feedback will be so-called will be a V positive, but the fact that the user has watched them before. So that's why I'm thinking maybe for the improvement of this paper, there might be a way that they should incorporate those items that the user likes, but they have watched it before. That's how I was thinking.
Okay, that's a good point. Okay, so we're done with this first paper, but I think if you have any questions, I'll let you spend a minute to ask. I think it's always good if you're not sure or you're not sure the differences about the model to ask. I've been compiling a Kahoot, so at the end of both papers, we'll have a chance to go through that as well. So please ask. It is a discussion group, so we still have about 5 minutes to discuss. Okay, I don't hear any questions. So I hope you guys will pipe up a little bit more for the second half, for the second paper. So again, let's thank Evan, Henry, and Zihan for giving this presentation and for our scribes to scribe. So we'll continue on to the next paper. Thank you, ladies and gentlemen. We'll go for the last paper of the semester.
Can you see my screen?
Yeah, Yong, we can see your screen.
Okay. Good afternoon, everyone. Our presentation is seamlessly unifying attributes and items, conversational recommendation for code start users. Firstly, I will introduce the motivation. In the past decades, most recommendation research has focused on static recommendation, such as advancing modeling historical user behaviors, proposing various methods like traditional collaborative filtering, content and context-aware filtering, and prevent neural network methods and graph-based methods. However, static recommendation methods suffer from some inherent limitation of performing real-time presentation for cold start users. In addition, online recommendation, for example, multi-unbounded approach addresses limitation by interactively exploring user preference online and causing the exploration and exploitation trade-off. However, exciting bandit-based methods model recommendation actions homogeneously, especially they only consider the items as the arms, being incapable of handling the item attributes, which naturally provide interpretable information of users' current demands and can effectively filter out undesired items. Therefore, in this paper, it considers the conversational recommendation for cold start users, where a system can both ask the attributes and recommend items to a user interactively. Then I will introduce the problem setting. Multi-round conversational recommendation. The system can perform attribute asking and item recommendation multiple times until the recommendation is accepted or maximum number of turns is reached. The objective is to achieve successful recommendations with the fewest conversation turns for each could start user who has no past historical interaction records. We use V to denote all the items, P to denote all item attributes. In each turn T, the system maintains two candidate ports, one for items and another for attributes, from which we select attributes to ask and top K items to recommend, respectively. As shown in the figure, the left one shows the interface of the chatbot in Taobao. When a user comes into the system, the bot can ask questions to elicit user preference, such as asking the user preferred attribute. After several rounds, the bot makes recommendations according to the user's responses. Thompson sampling. Thompson sampling is a typical class of bandit algorithms, which balance the exploration and exploitation during online learning. Here, the exploitation means taking actions according to the model's current estimation, the user's interest. And exploration means exploring a user's unknown preference to possible higher reward in the future. Thompson sampling balances the exploration and exploitation trade-off by sampling from a posterior distribution of the reward estimation. The figure illustrates the whole process of the proposed conversational recommendation for course start users. This figure focuses on the course start recommendation. Therefore, we need to firstly initialize the distribution of user embedding. Then we can sample user embedding from the distribution. After that, we need to calculate the reward value of each arm and choose an arm to play. Then we will ask attributes or make a recommendation based on the selected arm. After that, we will obtain feedback. And finally, we use the feedback to update the estimation of user embedding. Firstly, I will introduce the initialization and sampling. And for the arm embedding initialization, we train an offline factorization machine model to simultaneously get the embeddings of all attributes, items, and exciting users. For the initialization of preference and embedding of users, we hypothesize the historical action of exciting users can help to estimate the preference of new users. Without any previous information, it is reasonable to assume that the preference of new users to be the average of exciting users. Thus, we initialize preference embedding U as the average of embedding of exciting users. Okay, Ruofan will introduce the next section.
Okay. So given the user embedding sample from last step or the limited chat context we have, as an agent, we need to take an action A. Our action could either be we ask user's preference about an attribute. For example, here we ask, do you like videos for education, beautiful women, or religion? So here, education, beautiful women, religion are attributes. An action could also be we directly recommend K items. In these examples, the specific videos to be recommended are the items. So here, we want to choose an action A to maximize reward R. The best action A is selected by solving the following optimization problem. Let's look at the first term. The first term is the dot product between U and XA. U is the user embedding sample from step 1. It can be seen as the current estimation of users' item preference. XA is the embedding for a particular action A. So the first term describes how much an action is aligned with U. The basic intuition is that an action is selected when it is conformed to user's preference. As for the second term is the sum of dot product between XA and PI. XA is the actual embedding, same as last slide. PI is an attribute that user is known to like from chat history. So the second term actually captures how much the action A is aligned with PU. The intuition here is an action that is within users' known preferred attributes is highly likely to be selected. So the overall intuition is we select action based on users' item preference as well as users' attribute preference. For example, our PU could be, we know that a user likes a particular type of movie called suspense movie. And from chat history, we also know that users have rejected our recommendation on 2 particular movies. So a possible action to take at this time step is maybe we will recommend another suspense movie. Once the action is chosen, user will provide feedback to that query. User's feedback could either be accept or reject. If the queried attributes or the recommended items are rejected, then we need to update our PU and U. U is the estimation of user embedding. If the queried attribute is accepted, we also need to update PU and U. On the other hand, if the recommended items are accepted, then the dialog is successful. So we end the dialog. When update happens, we are updating current estimation of user preference U and the preferred attribute set PU. For PU, the update is quite simple. We just add attribute into PU. But when updating U, we need to update the sampling distribution for U asserted in step 1. The new inverse for the sample distribution U is equal to the old covariance inverse plus the covariance for your action embedding. So the covariance for action embedding will have non-negative diagonal values. So you can imagine that the new covariance diagonal values is less than the old covariance diagonal values. In other words, the variance in our sample distribution will decrease, and this is as expected since we have more information about the user. The uncertainty in our sampling distribution will decrease. This is for the new covariance. As for the new mean, it will be shifted towards action times user feedback. What I mean is that if we take an action and receive negative feedback, then the mean will shift away from action embedding XA. On the other hand, if we take an action and receive positive feedback, then the new mean will be shifted closer to XA. Let's revisit the big picture again. When the chat starts, we have no information on that user, so we need to sample the user embedding from the average of population. Then from the current user embedding, we search for the best action to take or the best arm to play. After an action is taken, user will provide feedback. If the feedback is positive, we quit the dialog and mark the conversation as successful. Else, if the feedback is negative, then we need to update our estimation of user embedding and do the sampling and arm choosing again.
Thanks, Ruofan. So I'm gonna continue on with the experimentation stage as well as the results of this paper, and this will just be a brief overview of the results, which are numbers here. But I will also be talking about a few interesting case studies to actually see what the system is doing and how it is performing against other type of similar systems. So let's dive into the experimentation stage. So the team used 3 different data sets in order to do that task. Yelp, Last FM, and a new data set constructed from this website called Show. I'm sorry if I didn't get that name correct. The third one is based on video clip records of a cold start user, and a picture was shown earlier. So it's similar to when we enter any new website and it asks us what are the topics you like. So a new data set was constructed and used for this. These 3 data sets were combined together and split in the ratio shown in the slide. And the evaluation metrics used were success rate primarily. Success rate, which this paper is using, is success rate at 15. So 15 turns. And it also uses the average number of turns to end the session, which is 80. Next slide, please. So these are the results of the system. The first three important rows are the baselines. Because these baselines will be explained or will be used for the case studies as well, I'm just going to briefly explain what these are. So the first baseline is ABS greedy. It's similar to the initialization step of our model. So if you guys remember the first in the method, the first stage of our process is initialization, which is using an offline factorization machine model in order using existing system records. So it uses existing user records to create a sort of initialization step. So that's the baseline which we are looking at. If you also remember, we are using Thompson sampling to maintain EE balance. And so that should technically be the baseline which we are comparing against, because we are using Thompson sampling to improve our results. But prior research has shown that this method, ABS-greedy, works better than Thompson sampling in all different cases. So that's why this is selected as our first baseline. The second one is conversational UCB. So it is a more recently proposed paper to which is similar to which is similar to this method as well. It also applies bandit methods for the problem of conversational recommendation. The major difference between these two papers is that conversational UCB does not maintain the exploration exploitation balance, unlike this paper, which does. And the third one is year, which was mentioned earlier today as well by Broughton as well as the others. So year, a bit of recap is just that it uses it's the current state of the art MCR model for warm start users. So that serves as a good benchmark to a good baseline to compare against as well. An ablation study was done by changing various units which were mentioned earlier. But an important thing to note is that the model given performs the best for cold start users. And yeah, the numbers are shown below. But something more interesting to look at is the next slide. Next slide, please. Yeah, in the next slide, we will actually be looking at some real life interaction records of how this system is performing against two of the baselines defined earlier, year as well as conversational UCB. And we can actually see how the system is different from these two. So the three cases we will be looking at are the first one is the user wants a video of a famous, beautiful female tennis player. So quite a few attributes to search in that. The second one is about the development of Buddhism in China, a religion, while the third case is just about and is more of an average user or a user who likes a video introducing a recently released movie. So let's dig into the first case study, case A. Next slide. So the two baselines, conversational UCB and year, if you can immediately spot a difference between these two as well as our system ConTS, it's the number of questions asked. And as stated in the introduction to this paper, we wanted to reduce the number of questions asked in order to give a recommendation, which is kind of the objective. So this works really well for a cold start user as defined here. Some of the reasons why this is as such is that for the first model, conversational UCB, how it works is that it is in a way hard coded to ask at least to at least spend 4 turns while asking questions in order to get a good idea of what the user's preferred attributes are. So even after the first two questions, do you like videos for beautiful women? And do you like videos for sports? Which is the answer to which is yes. It is actually the perfect time to recommend ideas to the user because you already know what the user is looking for. But because the system is hard coded to ask more questions, it continues asking additional questions for which the user rejects and it then recommends items. So that's an area where our system is much more flexible in that it just needs to ask the first question, do you like videos for arts? And once it rejects that, it immediately moves to sports. And yeah, then we found a similarity and we can start recommending items. So it's much more flexible than conversational UCB. And in comparison to Year, because Year uses historical interaction records of existing users, it tends to start off with some more popular attributes. So one of the most popular attributes which users would like is movies, and it continues on in that line. So movies, animations, teleplays. When the answer is no for each of these, it kind of narrows down its search space, and yeah, it recommends something, but it does not exactly capture what the user wants. So in this typical case scenario which we are presenting, the system conversational ConTS is performing much better compared to the other two. So this case shows the merits of our models, but there can be cases where ConTS does not perform as well as the other two as well, which we can see in the next couple of cases. So next slide, please. So yeah, for case B, which is talking about a deeper topic called which is religion, or religion is a topic which is is one of those topics which is hard to infer because it is not too popular. We can see that conversational con UCV will have the best performance in this, and it is the only one which actually recommends it is the only one which recommends religion the fastest here because of its rule-based policy. So as I mentioned earlier, it typically asks questions for the first 4 turns, and it is able to infer enough information about the user's use case, which is religion in this case. However, our system is not so patient, right? Because it wants to recommend something immediately, or it does not wait enough turns in order to ask the user. It wastes a couple of turns in recommending things, but it still reaches in the end, but just at a later time. So some turns are wasted in that case. And in Year, we see another case where it is not able to solve the problem for a cold start user. So it is still falling into popular themes like music, animations, the previous stuff which we mentioned before, and it is not able to get into the correct answer at least quickly. And in the third case, next slide. So this is the most suitable use case scenario for Year because if the user likes something which is very popular like movies, you can immediately get a recommendation for that because it seems like a typical user who already who suits the average historical user interaction, which the system exactly does. So in this system as well, ConTS is taking a bit more time along with con UCV. But a thing to note is that this case study is completely against or completely the thing which we are not looking at, right? For a code study user, what we are going in is with the assumption that they might want something which is not so general or which might not be able to which we might not be able to get via historical user interaction. Yep. So I hope that these 3 case studies were good enough to kind of help to show the differences between these systems and how the system is actually working pretty well for a cold start user. And in the next slide, yep, I would just like to conclude that in this paper, what we've tried to do is that we've shown how this paper addresses the problem of cold start recommendation. And it does this by primarily unifying items and attributes into the same arm space. And yeah, a lot of different experiments have been performed, which show that this approach, ConTS, does outperform other state-of-the-art approaches in terms of the evaluation metrics which we have shown, which is success rate as well as average number of turns. And yeah, with that, we have come to an end of this paper's presentation, and we can open the floor for questions or discussion.
Okay, thanks, Shreyas, and everyone for presenting, to Yong and Ruofan for presenting. Do we have questions? So this is a nice paper because it's extending the year framework as the previous work. So maybe we can get some comments from all of you. So, okay, I'll start off the questions, but I hope some of you will participate. I mean, this is a discussion group, so I hope at least the scribes who are responsible for scribing this paper can weigh in with their comments about the paper. You know, one of the key things here is about the attributes versus items, right? So when we're talking about the attributes, we can think about attributes that pertain to a lot of items or to a few items, right? So what type of implementation details do we have to consider in this paper to consider which attribute to ask on? How do we determine that? Yeah, maybe we can start with that easy question. So Shreyas, maybe you can try to start.
Yes. So how the question space is selected. So as I might be wrong, correct me if I'm wrong. Is that so? What you mentioned is that the attributes and item space. It is important to ask questions which will cut down the space. So it's either because we are kind of narrowing our search into a particular attribute. I think that we will first start asking those which have a lot of possibilities, and if it is rejected, we trim down and go into narrower fields. Similar to the example of the case study of religion. That's you start off from stuff like movies and slowly head down to more particular things. That's what I gotten from this paper.
Okay. So let me reflect this to the rest of the people in the group too. You know, so we start from fairly general attributes and we ask because we think the utility is higher, and we go with smaller groups later. Do you think there's a use in starting with something else for particular types of people, and how might you implement that? So we'll ask other people to think and answer. So Shreyas, you're off the hook for this one.
I guess if it's some kind of like social, I mean, if it's some kind of like platform like maybe Netflix, like usually when you register, you're usually asked to indicate like what attributes or like genres you're interested in. So I guess in an implementation, you could use those to somewhat aid the conversational recommendation, because you already do have a little bit of site information.
So that's expressed from user preferences from earlier rounds, right? So yeah, they can definitely be fed into this case. So how might that help us better select? I mean, it could be just through matching the previous preferences, which we can regard as historical information that we're pulling into the session. Are there other ways that we could incorporate that side knowledge? So thanks, Evan, for that. I want you guys to think about this a bit more.
I'm just taking a guess here, but
Okay.
one of the earlier intuitions I expressed was like of thinking of it as a distribution and of like with rounds constraining the variance to be smaller and shifting the mean. So if I think about it that way, we still need to have some sense of like when you get a negative hit, like you ask a question and it's a no from the user, you get negative feedback, you still need information on the direction you want to shift the mean. So that prior information can be incorporated, like to try and guess the best exploration direction you want to shift the mean.
Mm-hmm. Any other comments about this before I shoot off another question? I think eliciting preferences is a really important part of recommendation. And I'd like to have you guys reflect on how you decide preferences and elicit other people's, interests, as you will. Because I think there's such a thing as people who are eclectic in their tastes in a particular aspect. So when it comes to that, they show proclivities for small sets of items that are not mainstream. I mean, you can think of music or movies in that sense, right? So if you know somebody it has that type of historical information or starts to prefer information that is not like normal, like Shreyas was showing us, a difference between somebody who has common mainstream popular tastes, let's say, I don't know, what was the first example? Beautiful women tennis players or something like that. I don't know whether that's a common preference. I guess it is. And then a case of something more niche, like people who want to watch particular religious videos. Again, perhaps that's true, perhaps it's not. Then how would you want to perturb your strategy for recommendation or for asking attributes in a way that this paper or the others don't really cater to? And as a side question from that, are there domains in which this type of eclectic tastes are more prevalent than others? Or are there cases where there isn't that type of preference, like, standard entropy reducing means like this paper using multi-arm bandits and Thompson sampling would be sufficient to get an optimal strategy? Come on, guys. I hope you had your coffee. Come on.
I think at least about the question regarding like whether this differs across domains, I would say like most likely it's likely that it differs widely across different domains. Suppose you think of a recommendation problem in the academic research space. You want to recommend a paper that an academic is likely to read. It's going to be very hard to, because a person is likely to be interested in interactions of specific concepts in like many domains. It's going to be very hard to pick out which ones will be of interest to the user. But this might not be true in other domains like music, that there might be broader categories like that define either the tempo or the tone or the instrument that can actually identify whether a person might be interested in that particular category of music. I mean, it's a bit vague, but I'm trying to understand, like, I'm trying to guess how it would differ across domains.
Yeah, so that's a really good point, is that when you think about items having rich content-based metadata, right, where the embedding or representation of an item could be quite interesting, right, have a lot of metadata consumed with it, that might be an area where there could be more developed tastes, right? And I'd like you to also think about this other aspect. Do you think that recommenders that have to deal with very item sets that are often consumed or seldom consumed would actually have a better effect from Thompson sampling, this paper, or not? There's no right answer. So I just want you guys to think about it and discuss on your own, or just give your idea.
I think maybe an example could be like for food, because I think for most of us, when we have like a general liking to a certain group of foods, that isn't something that changes very often, and it's also not of it's more likely that, like, if for example I liked Chinese food, I wouldn't like just one type of Chinese food amongst that whole category of Chinese food. So um I think for that, perhaps Thompson sampling would be useful.
Okay, so Evan brings up a good point. Like you might prefer a general category, but within that general category, there are subcategorizations. And then here you might prefer, let's say, a more diverse background. Like you say, you like Chinese food, but like, maybe Teochew or Cantonese or Szechuan, maybe you would have different preferences related to those categories, although they all fall under the general umbrella. I think there's still quite a lot of room for enlarging and relaxing the recommendation problem. And I have one other one for you in the Kahoot that we'll play right after this. Do we have any other questions that you guys want to discuss?
I
Shreyas?
guess general discussion topic I had in mind was so like one sentiment I get from friends is that at least, for example, YouTube, like it tends to be that like you you're comfortable with like the set of videos you're being recommended, but the moment you like watch something that your friend sends you, then that changes like the kinds of recommendations that you receive. But that's not exactly something that you would want to have. So perhaps if in this case, in the conversational recommendation system, I do feel like because it's iterative, it's possible for perhaps a user to say that, like, hey, the set of recommendations you're giving me right now is really good. So perhaps save it as something I could uh, like perhaps allow me a way to search for recommendations like those in future while still carrying on that conversation. That might be a useful feature, maybe.
Yeah, I think that's a good point. We really don't know how to interact with recommendation systems very well yet. I think Evan brings up a good point. Another thing that's very important is, the items that are in certain recommender systems, let's say Google's recommender system, which is their search system, and YouTube's recommender system for videos, they have such a large inventory of items. It could be that certain things no longer get recommended at all, in which that there is no utility in keeping that item around. Or it could be that it actually has utility, but because it hasn't been surfaced, it hasn't found the right audience through the recommender, you can't locate it. So one of the things that's interesting to look at is, does every item in a recommendation system, can it find an audience, right? If you have a lot of items in your inventory that are never recommended, then maybe it's time to prune them, especially from an e-commerce standpoint. So that's one thing. So Evan also points to the point that the way that we recommend is sort of very restricted. I mean, in all of these papers, we see a very mathematical and rigid definition of what it means to interact with a recommender. You can either accept the item or you can reject it. You can't say, well, postpone it for later, or I'm not interested, but I'm not really that sure. Could you show me other items? Can I come back to that item later? All of these types of real world niceties that people have when they're considering items are not really brokered in the mathematical underpinnings that we have right now, because, well, we like math. So we tend to construct things that are congruent with things that are solvable, because we have a class of algorithms and they solve certain problems very well because they have optimal properties, right? But other human aspects, we really haven't dwelled on long enough yet. Shreyas, did you want to say something as well?
Oh, I actually just wanted to ask a question about what would be the strategy. So your earlier question was one where if we wanted to know about a user's preference, is it very niche or is it a general thing? So if we do get to know that it's a niche topic like religion VR, which is the final destination, what would be the strategy to go for that? Or is there something different from these papers?
I think so. I mean, I think when we look at how people recommend, they have a good model of who they're recommending for. And it's not always going to take, let's say, the last preference or the last conversation, or, the set of 10 questions that Spotify asked you at the beginning when you signed up for the account, right? We are much more complex than that. And we have, lots of unrational behavior, which we have to learn how to cater for if we're going to make recommendation systems really interact with users in a satisfying way. So I don't know the answers to that. I think that's very much something that's worth exploring. And in our group, in Wing, we have one lady, Xinyuan, who's working on psychological aspects of recommender systems, because I think that is an area very worthwhile exploring, because we don't know. I'll also note that this is also a very dangerous area, because whenever you say nudging or persuading, right? There's the ability to have dual use, which means that you can use it for good or you can use it to harm people, right? You can say influence you into brainwashing you about certain things by only showing you certain things, right? That's what Facebook was already guilty of a while back, and I think to a certain extent there are lots of companies guilty of that right now. They just don't know it. That's the worst part, because there's nobody analyzing all of this data and showing that there are strong biases in the recommendation system. Their objective measure for optimization is the bottom line of the company, right? And so they're in folly. They just don't know it yet. So I think it's very important that we continue to do a lot of recommendation systems research and really think about not just the mathematical underpinnings, but really about the human niceties that need to be considered if we are doing this properly. Just because it's coded in an algorithm, that algorithm is mathematically optimal doesn't mean anything, right, with respect to whether it's suited for human consumption. Yeah. Okay, so we're going to end our session and the end of our reading group for the last 13 weeks. Thanks for joining us for the entire session. I'll just note as well that for those of you who, which pretty much is everyone in our group except for people in my group, who have done your project work on Wednesday, thanks very much for doing that. And I think some of you have slightly monetarily benefited from participating, so that's great. But I'd also like you to make sure that you have shown the hours that you have spent on the course so that I can approve your registrations. And I want to again give a big thanks to all of our external participants. You guys are the best because you are doing it without any compunction of getting any type of credit back, just for your own leveling up and helping out with all of our participants here in NUS. Okay, so the very last thing we're going to do today is play Kahoot. Okay, so you can go open a browser window. It's going to take about 10 minutes, so just key in the URL kahoot.it, and the game pin. And so we have, I think, looks like about 24 people on the call. So if we make it to 20, then we're all good. So bonus points if you can use emojis in your name. Okay, thank you, Zihan. Thank you, Vic. Oh, we have somebody who's only emoji. Okay, great. Can we make it to at least 15? Let's see. All right. Okay, I made these questions on the fly, so I don't know whether they're accurate. They're from my understanding of what you guys presented. Okay, going once, going twice. All right, let's go. So true or false, ECR collects and integrates user feedback in a one-shot manner. Okay, it doesn't, right? It's an incremental model. So it does have to go through several rounds. So we have Shinza, ST, and Evan in the front. Hoot in 4th place and Weicong in 5th place. Why does the ECR paper use a Gumbel softmax? I don't actually know whether our presenters went over this, but I included it anyways. Okay, so almost everyone got that one right. So I guess we did cover it. I didn't catch whether we did or not. So because you're using sampling, you have to form a distribution from that in order to use softmax and do a back propagation. So that's why we can't use the standard softmax. Okay, Weicong is at the top, ST and HK in 3rd position. ECR addresses which methods or method for collecting feedback. I think I coded this question wrong. I think it's coded as a single answer. It should have been a multi-select because I remember on the slide, there was what and whether, but of course it only does one of these. So it's the whether category. So many of you are right. Good job. So HK is in the front now. TK is catching up. How does ECR employ soft constraints? I think we covered this one enough times, so I think we can get it, right? Okay, maybe I made the answers too long for you to read. Apologize for that. Okay. Okay, so HK is running ahead. So I think that's Henry, so good job. This has to deal with this part of the presentation. So does the user concept importance of tally across information across items or users? I guess that's the question. Yeah, okay, so this is a cross attention part. So it's looking for information at the opposite side of the interaction data. Okay, HK is still in the front. Okay, next set of papers. Oh no, it's still on ECR. Okay, in ECR, what does the local view capture? Okay, I think you can interpret this two different ways. Okay, so I think most of us would have said it's specific to the user item pairings, but I think it's really more about a specific user. You know, you're looking at a particular user and you're trying to recommend things for that user. So it's going through all of the items that meet or don't meet the concepts that are there. So, I mean, if you put blue, I think you're also correct. So unfortunately, we only get one answer here. So I've gotten the red one as correct. Okay. 7 of 11. Thompson sampling is appropriate for multi-arm bandit because of what? Okay, so most of you got that. Yes, it's because we are balancing exploration with exploitation. We want to exploit when we have enough confidence. And when we're not sure, then we go explore and try to pull another arm. Okay, so looks like our leaderboard is still constant here. True or false? Does unifying attributes and items paper model the common ordering of questions? Okay, you guys were evenly divided. I don't think there's any specific explicit criteria to say that one question should come before another. So I think that is false. Okay, we have Weicong in the front, Shrug in the second place, HK in the third place, and Vic is climbing up. 9 of 11. Does either paper allow the user to express a neutral stance towards an item or an attribute? Hey, all of you thought that, well, at least you had an opinion. Okay, so I think there are definitely cases where if you're recommended an item, you have to say whether you like it or not, you know, accept or reject, and same with an attribute. If I'm wrong, please correct me, and then you can put it into the scribe notes that your prof got it wrong. Okay. QR has emerged on the leaderboard for the first time. Let's see. 10 of 11. This is our last question. I wrote this wrong. Sorry about this. This should say worse. Yeah, if you didn't answer so fast, you would have heard my clarification. So I think the answer is sometimes it's worse than the upper bound confidence measure. Okay, this is not an answer, so you can just write down what you think. Well, actually just select. Okay, so most people found the unifying attributes and items paper more clear. This is not to say anything about the teams that presented them. Maybe the concepts were a little bit more dense. I agree on the ECR paper. Okay, So that is it for our entire course. We have Shrug in third place. Topic Tundra, who made it up to the second place. And Weicong to take the lead in the podium for first place. And we have ST and QR in fourth and fifth place. Okay, so that is it for our course. Thanks so much for joining us for our reading group here in the web IR and NLP group at NUS. There'll likely be another reading group next semester in the fall in August. It really depends on whether our current and upcoming batch of students agree to be subjected to another grueling 2 hours every alternate Friday. If so, then you'll see us again, and hopefully you can join us for that. Winners for our steps participation on Wednesday, please do remind you to update your bank account details, and please send me your hours for all 6101 participants as well as DYOM. Okay, thanks very much. Good luck on your exams and your finals and your projects and your assignments, and good luck sleeping too. Okay, bye now.